So hello dear students, now in the last subunit of this chapter we are going to discuss some problems based on radioactivity. So whatever we have discussed in the previous subunits on the topic of radioactivity, it will be applied here when we solve the problems on this topic. So let us first do the first problem. The question number 1, which is given in S.N. Ghoshal, the book on nuclear physics. The variation of the rate of beta particle emission from a radioactive sample with time is given in the following table. So this is the table given in which the rate of emission, or the activity you can say, with respect to time is given. So at time t is equal to 0, the activity is this, the rate of emission is this. At time 10 hours, it is 1458 and so on. So what we have to do, we have to plot a graph of the logarithmic to the base 10 of the rate of beta emission with time and determine the half-life of the sample from the graph. And what is the decay constant? So we have to calculate the half-life and the decay constant from this graph between the log to the base 10 of the rate of beta emission with time. And as you know, the log of activity with respect to time is a straight line with a negative slope, as we had done in the previous subunit. So we will see it here how it happens. So this is the given data here. So we have reproduced the data here, which is already given in this table. Now what we do is we calculate the base 10 logarithm of the emission rate. So the emission rate is given here and we calculate the log 10 of the emission rate. Then we plot log 10 of the rate versus time, and it should be a straight line for the exponential decay. So what is the equation for the logarithmic? So log 10 of the rate is equal to log 10 of the R naught, which is the rate at time t is equal to 0, minus lambda divided by ln 10, natural log of 10 times the t. Now this is the equation. Basically you just take the log 10 of the exponential equation for the rate, which is given by the Rutherford-Soddy law, as we have done in the previous unit. So you have the Rutherford-Soddy law. You can take the logarithm to the natural base e with respect to that, and you can calculate a straight line, or you can get a straight line expression for that. But you can also do it for the logarithm to the base 10, and only thing you require is the conversion factor here, which is ln 10, the logarithm to the base natural e to the 10. So this is the conversion factor which converts log to the base 10 to the log to the base e, or the natural log. So you have this conversion factor here. Rest of the equation is just the same. And since you have this equation, and you know you calculate log 10 to the rate of the rate, and you calculate this t you have here, and you plot it. So if this is the equation of this graph, then lambda minus lambda by ln 10 would be the slope of this graph. It would be a negative slope, and the value would be minus lambda by ln 10. So then lambda would be minus the slope into ln 10. So if you plot the graph, calculate the slope, and then you multiply it by ln 10, then the negative of that would be equal to lambda. So here what we do is we take the time from 0 to 95 hours, we take the rate, we calculate the log to the base 10 of the rate, which is given here, and then we plot time versus log to the base 10 rate. So time on the x-axis, and this table, that is this quantity log to the base 10 of the rate, on the y-axis. And then slope would be given, which is turns out to be equal to minus 0.0155, and the decay constant is basically, as I have told you, minus slope into ln 10. So it is going to be, if you calculate ln 10 and then you do this calculation, you will get 0.0357 inverse of hour. And what about half-life? Since I have told you in the earlier subunit that half-life is ln 2 by lambda, So just if you have the value of lambda, you can calculate the half-life. Using the value of ln2, and you have ln2, you divide it by lambda, you will get the half-life. So here we have the plot of log to the base 10 of the rate versus time, and you can see it's a straight line, and time is given in hours on the x-axis, and the logarithm to the base 10 of the rate is given on the y-axis. And you can see you have a straight line with one exception which you can neglect. At time t is equal to 80 hours, the data that is given for the rate is not matching the rest of the data, and so it is an exception and you can neglect it. So the slope is just when you attach all these points together and then you calculate the slope of this graph. From that you can calculate the value of lambda, and from that you can calculate the value of t half, as we have done in the earlier slide. So another problem which is also given in SN Ghoshal. So you have 3.25 microgram of radon gas, 222 Rn, and it is separated from a certain amount of radium, 226 Ra, and this is basically, these two samples are in secular equilibrium. So the radon gas is in secular equilibrium with radium. So, and then in that case the half-life of radon and radium are given, which is 3.84 days and 1620 years. So you can see that the parent, which is radium, has got a very large lifetime or half-life, which is 1620 years, and radon has got a very short compared to radium. The half-life of radon is just 3.84 days. So it is much smaller than the half-life of radium. So in that case, a secular equilibrium will be established after a long time. So then what is the amount of radium in that point when the secular equilibrium is established? So simply what you do is, you know, the activity of radon would be equal to the activity of radium under secular equilibrium, and activity of radon is equal to lambda, the decay constant of radon, multiplied by the number of atoms of radon. Similarly, the activity of radium would be equal to the decay constant of radium times the number of nuclei of radium. So you can see that NRA over NRN is equal to lambda Rn over lambda Ra, which is equal to half-life of Ra divided by half-life of Rn. Okay. Now, of course, you know the half-lives, 3.84 days and 1620 years. So just substitute that here. You can get the ratio of NRA over NRN. Okay. And now you want to know, since you know the amount of radon, which is 3.25 micrograms. So from the amount of radon which is given in micrograms, you can calculate the number of nuclei or the number of atoms of radon, and from from that, using this equation, you can calculate the number of atoms of radium, and from the number of atoms of radium you can calculate the weight of radium or the amount of radium present in this mixture. So this is a detailed calculation. The mass of radium mass of radon is 3.25 micrograms, which can be written as 3.25 into 10 raised to the power minus 6 grams. Molar mass of radon is 222 grams per mole. Of course, 222 is the atomic mass of radon. So 222 grams per mole is the molar mass of radon. T half-life is for radon is 3.84 days, and for radium is 1620 years, which can be converted into days like this. You multiply the years by the number of days in a year. So it is 365.25 days. And so from there you can calculate moles of radon. So moles of radon can be calculated by mass of radon divided by the molar mass. So the moles is 1.464 into 10 raised to the minus 8 moles. So these are the moles of radon. And from the moles of radon, you can calculate the number of atoms of radon. So that is just equal to the mole times the Avogadro number. So N into Na, which is the Avogadro number. So 1.464 into 10 to the power minus 8 into 6.022 into 10 to the power 23, which gives us 8.815 into 10 to the power 15. This is the number of radon atoms. And the ratio of half-lives, as you know, the half-lives are given, so you can calculate the ratio of the half-lives, which is 153,952.73. So the ratio of half-lives is equal to the ratio of the numbers of the atoms present. So from there you can calculate, since you know the number of atoms of radon, the number of atoms of radium can be calculated by multiplying the ratio of half-lives by the number of atoms of radon. So half-life, as you have already calculated here, you multiply it by the number of radon atoms, which we have already calculated. You get the number of atoms of radium, which is 1.358 into 10 raised to the power 21 atoms. Now the calculation again is very simple. After this, once you know the number of atoms, you can calculate the moles of radium, which is you divide it by the Avogadro number. So you get the moles, and from the mole you can get the mass. You have to multiply the mole with the atomic mass, and then you can get the mass of radium in grams, which turns out to be 0.510 grams. So the final answer is the amount of radium-226 present is approximately equal to 0.510 grams.